chapter 2, we've been doing the kinematics of one-dimensional motion. We've been defining displacement, we've been defining distance, velocity, speed, and we're finding the average speed, average velocity, average acceleration. Then we're graphing position versus time, we're graphing velocity versus time, and we're graphing acceleration versus time, and so on. Now, we're going to concentrate on particular cases where the acceleration is constant. These are this is a specific subset of one-dimensional motion where the acceleration is constant. So then we develop equations of kinematics for constant acceleration motion. And then there's a whole host of problems that you will see where the acceleration is constant. And once you know that the acceleration is constant, you can use these equations of motion. Only when the acceleration is constant, you can use these, okay? So then we're going to do free fall, which is another classification of a set of problems where you throw something up and then it comes back down. That also cases where acceleration is constant, but it's in the vertical direction, okay? So, and in these problems, usually, they're not going to ask you to graph anymore. So we're not going to do a full-blown set of questions like find the average acceleration, average velocity, average speed, graph A versus T, V versus T. So we're not going to ask you to do that. Usually the kinematics problems in this category, they're going to ask you, there's going to be some kind of situation. For example, there's going to be, let's say, a car, and they might give you the initial velocity of the car, and let's say it's headed towards a tree, and they might give you the distance to the tree, and then they might ask you a question such as, what should the acceleration of the car be if you're going to slow down, right? So what should the minimum acceleration of the car be so that you barely hit the tree? You know, like you go and just before you hit the tree, you stop. So these kinds of questions, there's always going to be certain quantities that are given to you, and you're going to be asked to solve for one or two other quantities. And they're not going to ask you to graph anything, usually. You're not going to be graphing X versus T, V versus T. You know, they could ask you to graph, but not really interested in the graph per se. They're usually interested in some unknown quantity. So this is one category. There's multiple kinds of problems that you can have in this. So let's first develop the equations of constant acceleration. So if A of t is constant, therefore A of t is equal to just A. Well, if that's true, then how does the velocity of the object change as a function of time? So here's how you develop the equations of motion. You see, A is equal to dv dt. Okay, A is equal to dv dt. And then if the A is constant, therefore it has no time dependence, the dt goes over there, and you can integrate this, both sides, and you get here v as a function of t is equal to at plus some constant, okay? And that constant is actually the initial velocity, okay? So v at any time is equal to at plus initial v. This is only true, mind you, if A is constant. This is written as usually V final is V initial plus AT. So this is the first equation of linear kinematics. Okay. Then we're going to do the next equation. Then we say V of t is dx dt. Okay. And then now you want to take the dt over there and integrate both sides. And you get x as a function of t is equal to, and the integral of this is at squared over 2 plus v initial is some constant, so the integral of is v initial t plus some other constant whose meaning is the initial x. Okay, that's the initial x value. So this is the second equation of kinematics. X final is equal to x initial plus v initial t plus half a t squared. Okay. And then I can, the third equation of kinematics, I can combine the two of them, and I can get rid of A. So from the first one, from number 1, I can solve for A, and I can substitute that into a second equation. So you get so x final equals x initial plus, so I substituted A into the second equation, and then one of the t's cancels, and I'm left with x final equals x initial plus v initial t plus, and then here you can multiply this in, half v final t minus half v initial t. Okay, so then v initial t minus half v initial t is half v initial t, right? So then I can factor out the half. I get I can factor out the t also. I get v initial plus v final. So this could be my third equation of linear kinematics. X final equals x initial plus t over 2 v initial plus v final. Okay? And now notice each of them has a particular advantage. Like, for example, in the first one, the advantage is there's no reference to x. So if the problem is, if they've given you v initial, they've given you a and t, they want you to solve for v final. So that's the quickest way to do it, you know. If you're not given x and you don't care what x is, the first equation is the first one, the best one to use. So this one is missing x. This one is missing what? V final. That one is very common. It's very, very common that we don't know V final and we don't care what V final is. So the second one is very used, very, very used. Okay. The third one is is missing an A. Sometimes that could happen where we don't know the A and we don't care about the A. All we need is the V initial, V final, and maybe they're asking for T, and they've given us X and V initial, and they've given us V final, so we don't really care about the A. Okay. Now we need one more. We need one that doesn't have the T. Some instances, there are cases where we don't care about the T, but we have the other. So I can eliminate the T here and substitute it into this T, or substitute it into this T, either one. This is probably easier because it doesn't have a T squared, you know. So eliminate the T from the first one and substitute it into the third one. So from the first one, we have T is equal to V final minus V initial over A, and then substitute that into the third one.